Got it. So hello everyone, welcome to the Quantum QBC Seminar. So it is our honor to have Roman Krems with us today to share his exciting research. So Roman is a professor of chemistry and distinguished university scholar at the University of British Columbia. He is also a fellow of American Physical Society and a member of the College of the Royal Society of Canada. So Roman is also a computer science, is also a member of the computer science department at UBC and a principal investigator at the QMI. So his work is at the intersection of quantum physics, machine learning, and chemistry on problems of relevance to quantum materials and quantum technologies. So he is particularly excited about the applications of machine learning for solving complex quantum problems and the application of quantum hardware for machine learning. I think today he is going to tell us something more about some quantum computers and machine learning today. So here's on stage. Thank you, Roman.
Oh, thank you. Thank you. I guess guys in the room, you didn't hear any of that, but you haven't missed anything. I'm going to begin by thanking you all for sharing your afternoon with me and for inviting me to present this work today. So I'm going to be talking about the interplay of machine learning and quantum computing today. So we're going to be talking about quantum machine learning in particular. So we may as well begin by defining what quantum machine learning is. So I will define quantum machine learning as any machine learning algorithm that uses quantum computers for any part of the algorithm. Okay, and then the goal of quantum machine learning a lot of times will be to perform computations that cannot be done with classical computers alone. That's typically the ultimate goal. Okay, we're going to be talking about supervised machine learning in today's presentation. So supervised machine learning deals with input-output pairs that are used to make predictions at an unseen part of the input space. So you start with inputs, you pass them through a model, and the model makes predictions. And of course, the model is trained by data. Okay, so the inputs are variables collected into multidimensional vectors. For example, they can be your parameters of your experiment. And the outputs are quantities that you want to predict. For example, in the context of physics experiments, this could be observables. Okay, more specifically, the two types of machine learning models that we're going to be discussing today are classification and regression models. In the case of classification tasks, the outputs of the machine learning model are binary, okay, yes or no, plus or minus. In the case of regression models, the output is a continuous variable. Okay, I've already mentioned that data is critically important for training the models. And I'd like to, when I think about machine learning in general, I like to categorize machine learning into small data and big data problems. Now, small data problems, they aim to build models that infer more from less. So the goal of building the best small data model is one that will provide the most accurate predictions with the least amount of data. And this is, of course, relevant for cases when data are expensive. Big data problems, on the other hand, aim to build models that scale well. Now, in physics and science in general, I would argue that data come from the solutions of complex equations or from experiments that are difficult to perform or difficult to obtain. So data are generally expensive, and the focus should be on making physical predictions based on small data. Okay, so the question that is in front of us now is, can one build physical machine learning models based on small data? Okay, now what is physical in this context? Well, again, if you think about a machine learning model that makes predictions as functions of physical parameters, this could be the parameters of your experiment or the parameters that define the Hamiltonian of a particular quantum system. Okay. Now, if you build a machine learning model that is able to interpolate, in other words, predict the quantity on output within the range of the input data, as well as extrapolate, and that is to predict the desired quantity outside of the range of the input data, then I would argue that the models that you're building are physical. Okay. So our goal is going to be to build models that infer more physics from less data. The question then is how? So I would argue that the best way to go about it is through the following two ingredients. First of all, you want to be working with kernel models because kernel models are mathematically better grounded. And then you want to work with the Bayesian version of the kernel models, because what the Bayesian framework is going to offer you is a way to select the best possible kernels for limited data problems. And then, of course, in the context of today's presentation, we have to ask if quantum computing can help towards this goal. And we can formulate specifically the questions that we're going to discuss as whether quantum computing can offer quantum kernels that can achieve better inference than classical kernels. And the second question that we often ask is whether quantum models can solve machine learning tasks that can't be solved classically. I will address both of these questions in my presentation today. So before we begin, let's briefly discuss how machine learning in general, kernel machine learning in particular, works. Okay, at the core of machine learning is basically linear regression. Pretty much everything that we do in machine learning boils down to linear regression. And how do you build linear regression? Well, you've got a bunch of data, and what you do, you build a linear function that minimizes the functional that's shown on the screen up there. Okay, so the second term here is very important for building stable regression models. What it does, it regularizes the model. So this term is referred to as regularization, as the regularization term. Okay. Now, so by doing this, you build a line basically that goes through the data. Okay. Now the problem is that the reality, of course, is most often nonlinear. However, it can be linear. Like in this particular example, if we were to make the transformation from x to f of x, with the f of x specifically being x times sine of x, then the function represented by the data in the upper graph here transforms into the distribution of data in the lower graph. And then you can perform linear regression on that data and transform it back to yield, to obtain the curve, the nonlinear curve that passes nicely through the data in the bottom graph here. The problem is that we don't always know this mapping between x and f of x. As a matter of fact, most of the time we don't know this mapping. Okay. Now, what kernel methods allow one to do is to build regression directly of nonlinear functions. And when you do that, you basically minimize a similar functional, the one that's shown in the bottom equation here, with the difference being that the regularization term is now represented by an inner product of a vector in some high-dimensional Hilbert space. Now, what's Hilbert got to do with this? Okay, so Hilbert, back at the beginning of the 20th century, what he did, he showed that the integrals over two real-valued square integrable functions, f and g of x, they have the same properties as a scalar product of two vectors in a Euclidean space, which means, for one, that for orthogonal functions, the integrals of this sort are going to vanish. Okay, now let's consider a particular integral transform as the one shown by the equation at the top of the slide here. So the word kernel, it comes from, I guess, the mathematics of integral transforms, which is, basically kernel is the same as the nucleus of a transform, right? So the kernel of this transform here is symmetric in x and y. So Hilbert's discovery, it basically implies that this kernel function here, the kernel of this integral transform, can be written in this particular form as shown in the second equation here, where phi of x, they're indexed by n. This is a set of functions, and they're functions of one variable, x or y. So these functions are orthogonal functions. So if these functions are orthonormal, then all of these coefficients lambda sub n here are 1. Now let's look at this decomposition of the kernel function as shown in the top equation here. This is actually quite a special function. And to see that, let's index it by x, and let's view it. Let's look at it as a function of y. Okay. Then you have the second equation here, which you may recognize as nothing else than a basis expansion of this function k sub x of y, with a sub x forming the coefficients of this basis set expansion. So this function, is represented by a vector which collects all of these a sub x coefficients in some abstract high-dimensional space. So we can then write any arbitrary function f of x as this sort of an integral here. It's very easy to show that this is the case. And then, of course, you if you believe Hilbert, then you associate this integral with the inner product between f and k sub x. So what we see is that any function f of x can be written as an inner product between f and k sub x. Now let's consider an arbitrary, because on the previous slide, on the previous couple of slides, we were talking about a specific k of x and y that satisfied the integral transform that I started with. But let's now consider an arbitrary positive definite function k of x and y. And when I say positive definite or positive semi-definite, I mean a function of x and y that satisfies this eigenvalue equation with the eigenvalues lambda sub n greater than or equal to 0. So the question we're going to ask now is, can we still write for any function f of x, can we still represent any function f of x by an inner product between f and k sub x? And the answer is yes. And this leads to the notion of RKHS, or reproducing kernel Hilbert spaces. Okay. Now, the answer is yes if we redefine the inner product of the Hilbert space. So the inner product of the Hilbert space will have to be defined as shown in the top equation here. Okay. And in this case, it's easy to show that the inner product of f with k sub x in that particular Hilbert space, hence the subscript h, gives the f of x. Okay. Now let me ask you at this point how you think about mathematical spaces. What defines a mathematical space? Like if I were to define a mathematical space, what would I have to define? What defines a Euclidean space as a Euclidean space? Well, in order to define a space in mathematics in general, we need to define its elements. A space is a set of some elements, but that's not sufficient. What we also need to define is the relationship between the elements. Okay. That's what's important about Hilbert spaces. So Hilbert spaces are known as inner product spaces. When people say an inner product space, they basically say that the relationship between elements of that space is defined by the inner product. Okay, so what we have in the top equation here is an inner product that basically depends on the kernel function, because you see you have this lambda sub n coefficients, which are the eigenvalues of the kernel function. If you look at the bottom equation here, the lambda sub n and the functions phi sub y, phi of y, they are, they come from the eigenvalue equation with the kernel function. So the kernel function here basically defines the way you would evaluate the inner products between functions in this Hilbert space. So the kernel function k of x and y, in other words, defines the relationship between the elements of the space. In other words, the kernel function k of x and y defines the Hilbert space. Now, again, if you look at the top equation here, you notice that lambda sub n, the eigenvalues of the kernel function, they appear in the denominator of this equation. Okay. Now, what if some of the eigenvalues are 0 or small? So that would become a problem, right? So we're going to come back to this question in a couple of minutes. Okay. Let me briefly summarize what we have discussed so far. Basically, what we're saying is that the function k of x and y is a kernel function of a reproducing kernel Hilbert space if it is a positive semi-definite function of two variables. Okay. Now, K sub x, we call it a reproducing kernel because any element of this space, any function f of x, can be reproduced by the inner product between K sub x and the vector that corresponds to that particular function in the Hilbert space. And what we also said is that the kernel function, if you know the particular mathematical form of the kernel function, then this defines a unique RKHS and vice versa. There's a one-to-one correspondence between the two. Okay. Now let's go back to this equation. Okay. So we see that the choice of the function k of x and y defines the coefficients lambda sub n, and sometimes those coefficients can be very small, and that's going to be bad because what that will lead to is the divergence of the inner products. We don't want that. Basically, what we're saying here is that the choice of the kernel function, it defines the RKHS, but some of those RKHS are going to be good for the learning purposes. Some of them are going to be bad. And I can schematically represent it like this. Like, let's say you have a target function that you're trying to infer from your data, and that function is shown by this white curve here. So depending on the choice of the kernel function, the RKHS is either going to include that function completely, in which case the function is going to be learnable, or it's going to include it only partially, in which case the function is not going to be fully learnable. So I guess the reason for me to discuss all of that is to illustrate that in essence, kernel machine learning boils down, like if you want to build extremely efficient kernel machine learning models, the question that you should be asking is how to find the right kernel for the particular data. So how to find the right kernel. So how do we do that? So given two kernels, given two mathematical functions for two kernels, how do we tell which one is better? Well, and this is where the Bayesian framework helps us. Okay, so we can define the probability, and this is what I have on the left-hand side of the first equation here. You can define the probability of the model. M sub I is going to be my model here, or the model is going to be defined by the functional form of the kernel function. So you can define the probability of the model given data. Now, the problem is that this probability in general is difficult to calculate exactly or directly, rather, but the Bayes theorem gives us the tool to calculate this probability, right? The Bayes theorem is the equation shown in the first line here. And if I now have, say I have two models, M1 and M2, and if I take the ratio of the probabilities of the two models, then on the left-hand side, I have this ratio here. On the right-hand side, I have this, okay? Now, the two terms, P of M1 and P of M2, they're called the priors. And if we have no prior knowledge about the models, we can assume that they're the same, okay? In which case, the ratio of the probabilities that we want to compute is given by the ratio of these green terms here. And what these green terms are, they're nothing else than the marginal likelihood. Now, the problem, so in principle, you can calculate the marginal likelihood. So if you know the model and you have data, you can calculate the marginal likelihood. But the problem is that in order to compute it, you have to integrate over all of the parameters of the model. And if you have a high dimensional model, basically the problem will boil down to, well, will require you to take very high dimensional integrals. So it's very expensive to calculate marginal likelihood. So in our work, we're going to approximate marginal likelihood by what's known as the Bayesian information criterion, okay? So, and if you have this, if you have a criterion to discriminate between two kernels, you can use it to build a complex model that sort of maximizes the amount of inference you can get from a particular data set. So how does this work in practice? Well, the way we do it is we start with a set of simple functional forms for the kernel function. Like what I've got here listed are 4 different functional forms for the kernel function. Okay. Now, each one of those functions could be used as a kernel, but that would not produce a great model. Okay. So what we do then, we start with these different functions and we start combining them. We combine them into products or sums. Okay. And then every time we combine these functions, we build a model and we calculate the Bayesian information criterion. And then we choose the kernel with the highest value of the Bayesian information criterion. Okay, so this algorithm can be depicted by this sort of a search tree, right? So you start with 4 simple kernel functions, you combine them into products and linear combinations, and then you choose the best combination out of those combinations, and then you iterate the process. Okay, and as you go down, deeper and deeper in this tree, the complexity of the kernel function increases, the Bayesian information criterion also increases, and the inference power of the resulting model increases. So this is the algorithm that was proposed in this paper here by Duvigneau and al. In 2013 for pattern recognition problems, and we have applied it to many problems in physics and chemistry, mostly for the purposes of building these physical extrapolation models. I'm going to show you on the one result that demonstrates how well this works, and this is for the example of the extrapolation of a 6-dimensional potential energy surface for the hydronium ion, H3O+. It's a 6-dimensional molecule. So, so the question is, can we predict the energy of the molecule at any configuration of the 4 atoms? Okay, so what I show here is a comparison between the quantum chemistry calculations shown by symbols and the predictions of the machine learning model shown by line here. And to build the model, we only use the data, the potential energies of the molecule in the shaded region here. Okay, and then we predict the energy of the molecule outside of the shaded region, basically in the entire configuration space. And as you can see from this graph, the models that we build, they can predict the energy of the molecule by both interpolation and extrapolation pretty darn well. Let me summarize again how kernel methods that we have been discussing so far generally work. So you start with inputs, you encode them into a kernel of an RKHS. You use that while you train this kernel by input-output pairs, and then you use these kernels in some sort of a machine learning model. And examples of machine learning models that are based on kernels would be support vector machines, kernel ridge regression, or Gaussian process regression. Okay, and then you use these models to make predictions. Okay, let's now talk about quantum machine learning. Okay, so in quantum machine learning, you would do essentially the same thing in the kernel version of quantum machine learning, except that you would encode your classical data into a quantum circuit of, for example, this kind. So then you operate with the gates of the quantum circuit on qubits, okay, and that will generate quantum states, okay. And by performing measurements on these quantum states, you're going to obtain some functions that, if you think about it, have all the same properties of the kernels of the RKHS. So you can actually build kernels, the quantum analog of kernels of an RKHS, by performing measurements on quantum states generated by operating with a quantum circuit on 2 qubits. Okay, and then these quantum kernels can be used in classification or regression models. We're going to be talking about classification models as usual. Okay, let me tell you in a little more detail how this works. Okay, so you're going to start with n qubits initially in state 0. Okay, you're going to introduce a sequence of gates that produces a quantum state. Okay, now these gates, they will depend on the data. You see, I'm putting the X in brackets here. These gates are going to operate on the qubits, but in a way that depends on the data. And then you're going to generate another quantum state that depends on X prime. And then if you were to take the inner product between these 2 quantum states, and in particular, if you were to look at the measurable square of the inner product, okay, this quantity here has all the properties of a kernel of an RKHS. Okay, so the question though is, okay, so if we can build kernels like this, this is another way of building kernels for machine learning, basically. But the question then becomes is, what is the best way to put the gates of this quantum circuit together to produce the most optimal kernel? Because if you wanted to build the quantum analog of machine learning models that would outperform the classical machine learning, you better know how to build the best possible quantum models. as well as the best possible classical models. Okay, so the question is, what is the best way? How do we put together the gates in this quantum circuit in order to produce the best kernel, or the most optimal kernel? Okay, so Elham Turabian, one of my graduate students, and we suggested this algorithm in this paper here that basically uses the same strategy as the one that I described earlier, except that instead of combining different functions for different simple kernels, we now combine quantum gates. Okay, and let me show you how well it works using the example of the classification problem that decides whether a perovskite, and a perovskite is a material with this chemical formula. It has 2 atoms of A, 2 ions B, and X, 6 atoms of X. Okay, and so let me show you the performance of a model that basically takes on input the size of the ions that make up a perovskite, and then predicts whether the resulting material is going to be a metal or not. Okay, so qubits now will encode the size of the ion, okay, in a given perovskite. And again, the prediction is going to be whether the perovskite is a metal or not. Okay, so what I've got here is a comparison of the classification accuracy between the optimized classical kernels of different kind and the quantum kernels that are built by this iterative algorithm that I described earlier. And the number of layers here, remember I showed you the search tree that builds up the complexity of the kernel. So the number of layers in that search tree now corresponds to the number of layers in the quantum circuit. Okay, and as you can see here, the accuracy that we obtain with the quantum kernel, the classification accuracy, far exceeds the classification accuracy that one can obtain with the optimized classical kernels. Okay, now what I've shown you is that quantum kernels can be constructed to offer powerful inference. The problem, however, with the algorithm that I've presented so far is that it's very difficult to scale it up, because as the depth of the tree grows, basically the complexity of the quantum circuit grows, and that of course brings with it a lot of issues. Okay, so is there a more efficient way to build quantum circuits, we would ask? Well, let me propose a radical idea. Okay, quantum circuits are isomorphic to polyatomic molecules, we say. Okay, so what Elham did in her work, she actually showed that you can map a quantum circuit on a polyatomic molecule, like the molecule of the kind I'm showing here, through a one-to-one correspondence. If you set up a particular algorithm of the mapping. Okay, now the question is, can the properties of the molecules, or the descriptors of molecules that's obtained, can they be good descriptors of quantum circuits? Okay, well, to demonstrate this, what I'm showing here is the separation of the quantum kernels into good kernels and bad kernels. Because, if you think back about how we build the quantum circuits for quantum kernels of our models, it's this iterative process that builds up the complexity of the quantum circuit, layer by layer. And in the process of this algorithm, we are generating a large number of circuits, and some of them are going to be good circuits. Some of them are going to perform better than the classical kernels. Others are going to perform worse. So we use the best classical kernel to sort of separate the good quantum kernels from the bad quantum kernels. Okay. Now what I'm showing here is the separation of the quantum circuits into the good and the bad quantum kernels, as a function of the 2 principal components that are derived from the molecular fingerprints of the molecules that correspond to the individual quantum circuits, in this process. Okay. So in cheminformatics, people know how to describe molecules with what's known as molecular fingerprints. Those are very high dimensional descriptors that, basically describe how atoms are interconnected in a molecule, the bond order, basically everything there is to describe about the molecule. So what we do here, we perform the mapping between the quantum circuit and the molecule. we then take the fingerprint of the molecule that corresponds to a quantum circuit, and then we reduce the dimensionality of the fingerprint by PCA, and then we use the principal components that's derived to basically characterize the performance of a quantum circuit. So what I'm showing here is the result of the description of quantum circuits by actually molecular fingerprints. Now, why do you want to simulate quantum circuits by molecules? Well, one reason is that we know a lot about how to handle molecular compound spaces. Okay, why do we know a lot about this? Well, because it's a very important problem in drug design, right? What you're dealing in drug design, you're dealing with a huge number of molecules, 10 to the 23 to 10 to the 60 molecules that form a chemical subspace for specific drugs, right? So given this number of molecules, you have to decide which ones you want to perform your experiments with for the purpose of, for example, developing a particular drug. So that becomes an optimization problem in a vast chemical compound space. And because it's such an important problem, people have developed many, many different techniques. And you know, I'm going to show you one example of a very efficient interpolation of molecular properties in a chemical compound space from our work. So this is the work of Don Mao, another graduate student in my group. And so what this shows here is basically the application of the algorithm that I described earlier, the application of the kernel algorithm that builds up the complexity of the kernel by maximizing the Bayesian information criterion to interpolating the entropy of molecules in the space of 133,000 molecules, okay? And what I'm showing on the right graph, in the right graph here, is the error of the prediction as a function of the number of training points, okay? So now chemical accuracy, that's the accuracy that people aim for when they make predictions of molecular properties. And this is the accuracy that is set by thermal fluctuations at room temperature, basically. So it's basically this shaded area here. So what I want to draw your attention to is the number on the x-axis here, which is the number of molecules that we need in order to train these models. So you see, like with as few as 100 molecules on input, we can predict the entropy of 133,000 molecules that have complexity that ranges from, in this particular case, from as few as 3 atoms to as many as 29 atoms. Okay. So why can we do this so efficiently? Well, because, well, first of all, we have this algorithm that we know how to increase the efficiency of, and second, we know you know, how to handle molecules because they consist of atoms, and there have been many different types of descriptors that have been developed for you know, the way atoms bind into molecules. Okay, so our current goal is to then take what we know about interpolating molecular compound space and design algorithms for optimizing quantum circuits by optimizing molecules. So this is something that's still work in progress, and if you invite me to give this talk a year from now, I will tell you about that. Let me now, before I finish, let me tell you about one other result of ours. So what we're saying here is that quantum machine learning opens the prospects for applications of quantum computing for interesting machine learning tasks. But the real question is, do we actually need quantum computers for machine learning? It's a question that is widely debated at the moment. Okay, so in other words, what we're asking is, can quantum computers solve a machine learning problem or a machine learning task that is not solvable on classical computers? Of course, when we say if something can solve a problem, we imply polynomial time. We imply that the scaling of the problem with the dimensionality is going to be polynomial and not exponential. Okay. Now, the answer to this question is provided by the work of Jonas Jager. So he's another graduate student in my group. So Jonas and I published this paper earlier this year where well, in order to describe to you the results of this paper, I have to talk to you about the computational complexity classes, okay? So as you know, in computational, well, some of you may know, in computational complexity theory, we have class P, which encompasses all problems solvable in polynomial time on a deterministic Turing machine. Okay, and then we have problems that are called NP problems, and these are problems solvable in polynomial time on a non-deterministic Turing machine. Okay, and then problems that are harder than NP problems, or problems that are as hard as the hardest NP problem and harder, they're going to be called NP hard. Now, if you have a problem that is as hard as any problem in a particular class, and if this problem is within this class, this problem is called complete, right? So if you have a problem that lies within this little intersection here, that would be an NP complete problem. Then we have a class of BQP problems. These are decision problems solvable in polynomial time by a quantum computer with probability of at least 2/3. Okay, so this class encompasses problems that are going to be efficiently solvable on a quantum computer. Okay, and then there is so we're talking about decision problems here, and then there is another class of problems that is hierarchically higher than BQP problems. And when I say hierarchically higher, I mean problem, class that will completely include all of the BQP problems, but that will also include problems that are harder than BQP. Okay, so this class is called promise BQP. Okay, and then of course there's problems that are harder than promise BQP, and those are promise BQP hard problems. Okay, so now problems that lie within this little intersection there are called promise BQP complete problems. Okay, now what Jonas did, okay, so he considered this particular problem that is known to be promise BQP complete. It's called the K-correlation problem, and the problem is actually very simple to formulate. So it's the generalization of the correlation problem, and what the correlation problem does, it asks this simple question: if you have two Boolean functions f and g, are they correlated or not? And correlation, what it is the correlation between f and the Fourier transform of g. Now, it was proven by other people, Scott Aronson in particular, that the K-correlation problem is a promise BQP complete problem. What that means, actually, is that if you were to design a problem with the same complexity as the K-correlation problem, and if you were then to design an algorithm to solve that problem efficiently, what you would be doing, you would be solving all of the problems in the promise BQP class of problems, as well, of course, as all of the problems in the BQP class of problems. And that's exactly what Jonas did. So what Jonas did in this paper, so he reformulated the K-correlation problem as a machine learning classification problem without loss of complexity. Okay, so, and then he showed that the resulting classification problem can be efficiently solved by the quantum analog of the support vector machine. Okay, in other words, by SVM with a quantum kernel. So what basically this does, it answers this question of whether quantum computers can solve machine learning tasks that are not solvable on classical computers in polynomial time affirmatively. Okay, so these are some of the papers that I have described today. I'm going to finish by, again, thanking the people who have done the work that I presented today. First of all, this is Elham Turabian, and I don't know, yeah, she's right here. And Dawn, this is Dawn's face here, as well as Jonas Jäger, who's standing right there in the back. So these are different pictures of my group taken at different instances of time. So I'm going to stop here, and we'll be happy to answer any questions you may have. Thank you very much. So I don't know how to handle questions on Zoom. I mean, like, is there a chat for that?
Thank you so much, Roman. We can take both chat questions, and also people can just unmute and ask questions.
Mm-hmm.
So, and it was asked about where this talk would be available, and it will be made available on the Quantum BC YouTube channel. after this talk. So I will post the link in the chat. So questions?
Thank you.
Thank you.
And remember, your question will be on YouTube.
In SFU, we have a question.
So,
Yep, you can ask.
it can hear me?
Yes, I can hear you.
So is the kernel machine learning is faster than the classical?
Faster. So again, so the statements that we're making here, well, there's several statements, right? The first one is that in principle, quantum machine learning does have a quantum advantage. So there will be problems that quantum machine learning or that quantum SVM can solve exactly in polynomial time that could not be solved with the classical algorithms in polynomial time. So that's the first statement we're making here. The second statement is that you can build quantum kernels for the quantum analog of both classification and regression problems. I haven't actually talked about regression problems today, but for both types of problems, you can build quantum kernels that offer better inference than classical kernels. Well, at least that's what we observe. But this is relevant for the limit of small data. And in this limit, you have to be careful when you speak about the quantum advantage of quantum machine learning, because in principle, kernels for a small number, well, kernels that are based on a small number of qubits, in principle, they are, they can be simulated on a classical computer, right? So, of course, as you increase the complexity of the problem to as few as, say, 20 qubits or so, it becomes extremely difficult to simulate those quantum kernels. But in principle, those quantum kernels should be simulable. Okay, and so all we're saying is that quantum machine learning for small data problems can be at least as good as classical machine learning. For some problems, you can actually have better inference accuracy, and the question is what to do with it. I mean, that's a question that we can maybe talk about and debate.
Okay, thank you.
So I have another question. So would the efficiency or the quantum advantage of those kernel methods depend on the properties of the quantum computer, say the connectivity or the post-selection or the continuous variable or discrete variable systems?
Yes, for sure. If the connectivity of the qubits, for example, is restricted, this will restrict the types of kernels that one could build on such a computer, right? And then, of course, there's noise and other issues that come with the actual gates. So all of which will affect the performance of the kernels. And yeah, the answer to that is yes. But the good thing is that we are at the age when we actually have multiple different architectures of quantum computers to work with. So there's actually a lot to choose from for this type of applications that I'm discussing here.
Thank you.
Anything else? Yes.
When you say efficiently solved by the SVM, like what do you mean, like polynomial time and cleaning data, or is it like polynomial time and
It's so you're talking about the K-correlation problem. Yeah. So basically what we're saying is that we can build the K-correlation kernel that solves the problem exactly in polynomial time. So the scaling of the time to build this kernel will and evaluate the kernel will scale polynomially with the number of qubits. That's what we're saying. And then if you were to do the same on a classical computer, so that scaling would be exponential. Now, the statement are only true when we solve the problem exactly. So the question we have to really think about and consider is what happens when we relax the requirements for the accuracy. And this is something that we're still working on to Yeah, so the question is, will the quantum advantage of quantum machine learning still be there when we relax the requirements for the accuracy of the classification? Because for practical applications of machine learning, we don't need perfect classification. Yeah. Anything else?
Yes, up to you to have that question. Yeah.
Can you hear me?
Yes, I can hear you.
Perfect. I wonder if you could speak to implementing these kind of algorithms on noisy quantum computers.
Yes. So we are currently working on that. So we're trying. It's not easy. We always run into issues. I mean, like some of the issues we run into is that the hardware efficient, combinations of gates are not the same as the ones that we need for building the best kernels. So that's the first problem that we often encounter. And then when we try to express our ansatz into the hardware efficient ansatz, then the hardware efficient ansatz comes out to be very deep and and impractical. So that's the first problem. And then of course the noise will affect what we're doing. We haven't gotten to the point of where I could tell you how and whether the current noise mitigation strategies can help. So yeah, hopefully in a few months I could have a better answer for that. But definitely we expect noise to be an issue. So right now, so what this presentation today showed is that in principle you can come up with quantum circuits that will offer better inference when used for the construction of quantum kernels than classical kernels. But once you start implementing the circuits on an actual quantum computer, so then you start running into issues related to some of what you said. And then so that to what extent this will be a fundamental problem, a fundamental issue, we have yet to understand.
Thank you.
You're welcome. Thank you. Anything else? Anyone?
Is that all the questions?
Yeah, shall we call it a day? I have another meeting.
Thank you so much, very much, Roman, for giving this wonderful presentation. And thanks to everyone for meeting in person and virtually. Thank you.
Thank you. Enjoy your day.
See you.